Have you ever watched a skater skate around and around in a skate park and think, why aren't they slowing down? Well, the answer is normals. Actually, the answer is pumping, but what even is pumping? Pumping is the act of pushing down into the ground as a way to increase your speed, like so. This is what my free body diagram looks like, but what's that arrow pointing up? That's the normal, a perpendicular reactionary force by a surface which counteracts forces going into that surface. If I increase my force into the ground, I can increase the normal. Okay, but I'm not going any faster. That's because I'm on flat ground. So why does this work in a bowl? First, we need to look at something more simple. This is a quarter pipe. When I pump, my exit velocity is faster than without pumping. But why is this? Let's look at three positions on a perfect quarter pipe: the top, middle, and bottom. If we take the angle the surface makes with the ground at these 3 points, we get 90, 45, and 0 degrees respectively. A free body diagram of me at the top of the ramp looks like this. However, if I pump into the ramp, that will induce a normal force. The normal is perpendicular to the surface, which points in the direction I want to accelerate in. Alright, so I have a force accelerating me after I pump at the top of the ramp, but what about the rest? Next, let's look at the middle. Now, the normal force is the sum of the normal due to the pump and the gravitational normal. If we construct a similar triangle, we can describe the gravitational normal as my mass times the acceleration of gravity times cosine theta. The total normal force is the normal due to the pump plus mg cosine theta. Another triangle shows us that the normal's x component is the normal times sine of theta, which accelerates me in the x direction I want. The normal due to the pump is directly proportional to the pump force applied. Therefore, as the pump force increases, so does the x component of the normal. This can be displayed graphically like so. As p, the pump force, increases, so do the values of the x component force. This increases the area under the graph as well. The integral of the force with respect to distance, in this case degrees, is work. Therefore, increasing the pump increases the force in the x direction and the work done, which gives me a greater acceleration and greater exit velocity. Finally, I'm at the bottom of the ramp. Theta is 0 and the normal points straight up, making it so there is 0 x component. This lack of a force with an x component is why I can't accelerate just by pumping into flat ground. So how can we apply this in a bowl? Well, if you look closely, each bend in a bowl is like its own quarter pipe, and a well-timed pump can increase your exit velocity at each bend. Whew, that was a lot, but I hope that the next time you drive past a skate park, you can recognize just some of the physics that are going on.